So the next set of instruction formats we'll discuss is the load store instructions. These interact with the memory and therefore they're important. So the format of the instruction is very similar to the MIPS instruction. So it is LW for load word, LD for load double word, LB for load byte, and LH for load half word. So LWRD offset, offset is a 12-bit offset. So you can think about why it is a 12-bit offset and not more or not less. And then followed by a base register, which is typically provided in RS1. So the format, for example, is like this: LWX964X22. So the immediate is 64, X22 is the base register to which you will add the offset, and then X9 is the destination register. So the way this works is you're going to take the offset, sign extend the offset, add that to the content of RS1. So for example, if this entire content is 2000, then you're going to go to memory location 2000 and then get the content of the memory location 2000 and store that in the register RD. In this case, store that in X9. So the 32-bit format for this instruction is given here. There is a standard 7-bit opcode, which is in the same location, 6 down to 0. Then you have the RD specified in the same location from 11 to 7. Then you have function 3 and RS1. All of this is very similar to the previous R format instruction. Just that now you have an immediate field, which is a 12-bit immediate starting from 31 down to 20. So that is the load instruction. There is also a store instruction, and the format for store instruction is quite different from that of the load. Now remember that in a store instruction, what we're going to do is the format is the same, but then we're going to be reading the content of a register, and that register is specified in RS2. So in this case, for example, if you consider this store X964X22, you're going to read the content of X9 and store that in memory location of the sign extended 64 plus X22. So here, there is no destination register because the destination is memory. So this is how it works. The destination is the memory because you're storing to the memory. Therefore, the two registers that you have, RS2 and RS1, are both source registers. We are going to read from both of them. So therefore, you do not have RD. And if you look at the load instruction, you have RD here. And in order to keep the format of the instruction consistent with the other instructions, so what they've done is they have the same opcode, 6 down to 0. Then you fill up the others, which is RS2, RS1, and function 3 in the same locations as we had for the R format. But then now you have an immediate field, which is 12-bit wide. So since we have occupied up to 24th bit in the instruction, we now split up the immediate field into 11 down to 5 and then 4 down to 0 and then split it up wherever there is the remaining space in the instruction. So that is how they have created this S-type instruction for stores. So now let us compare both of them. The I type, which is the load instruction formats are specified here, all of the load formats. Then you have the S type instruction for stores, and then you have the R type. So if you compare the store and the R type instructions, the RS2, RS1, function 3, and the opcode are all in the same positions. If you compare the store with the load instruction, then you have a part of the immediate field in the same position, and then you have the RS1 in the same position, and then the opcode, of course, is in the same position. So this is the comparison between the load, store, and the R type instructions. Then a couple of more formats are left. Now we have the important control instructions, which is the B format instruction for branches. So you have conditional branches and also unconditional jumps. So what are the branch instructions? You have the if else, while for, with check for certain condition and then jump to a different location. The format is, for example, if you're comparing equality between the contents of two registers, you have the EQ and then you have an immediate field. Now, what is the role of this immediate field? This is a 12-bit immediate and it's an offset. and this is a half word offset. So in MIPS, you have a word offset. So what you would be doing in MIPS is if RS1 is equal to RS2, then you would be jumping to PC plus immediate multiplied by 4. I think it was PC plus 4 plus immediate multiplied by 4. That is because this was a word offset, and therefore each word is going to occupy 4 locations in memory, because each location in memory is just 1 byte, and therefore a word is 4 bytes, and you'll occupy 4 bytes in the memory for a word. And therefore, if you have a word offset, you would be doing multiplied by 4. But then if you have a half word offset, this would be multiplied by 2. And also, the target address is not with respect to the next address, it is with respect to the current PC. That is the only difference they've made here for the RISC-V instruction format. So now the format for the B format is again uh, very similar to the R format, in the sense you have the RS2, RS1, function 3, and the opcode in the same positions as before. But then what is complex is the way they have split up the immediate field. Now the immediate field is a 12-bit immediate, so that is 12 down to 1. You can also call it 11 down to 0, but they chose to use 12 down to 1. So now the 12th bit is in position 31. That is, usually it is the signed bit, and therefore the split up the 12th bit here. The 11th bit goes here, 10 down to 5 here, and 4 down to 1 is in the 11 down to 8 position. Now let us see how to write this instruction. For example, if you have this loop, you're checking for the condition x1 is equal to x2, and if it is equal, you're going to jump to the last instruction which is specified at the end. Otherwise, you will continue with the next few instructions. So now how will you write this immediate field? Now the first thing to do is to see how many instructions later is the target. So this is called the target. So this is instruction 1, 2, 3, and 4 instructions. This is 4 instructions after the. So if this is our PC, so this is PC plus the number of instructions. So let us say this is PC plus, there are 4 instructions from the current instruction. Sorry, not the next instruction, but 4 instructions from the current instruction. So now 4 instructions. What does 4 instruction translate into half words? So each instruction is 1 word, because each one is 32 bits wide, or this is 2 half words. So half word is nothing but 16 bits. So 4 instructions means it is equivalent to 8 half words. So from the PC location, how far is the target, or how far is the target branch address? So this is about 8 half words away from the PC location. So therefore, our offset is going to be 8, because this is 8 half words. So now the way we will write the 32-bit instruction format is, we know the function and we know the opcode field. This is specified by the ISA. So the next thing, easy thing to fill up is what is RS2 and RS1. So you have X1 and X2, so we can fill that up. So RS1 and RS2 is 2 and 1 respectively. So the next thing to fill up is the immediate field. So the way we will fill up the immediate field is, we know that it is the offset is 8. In other words, this is nothing but the immediate field for our branch. And therefore, we'll first write down 8 in binary format. So I've written this 1000. So this is our 12-bit uh, immediate field. So this is nothing but you have these zeros followed by 1000. So this is the 12-bit immediate for our branch instruction. So now we have to split this up into this format. So this is immediate, the 12th bit, which is 0. Then you have 10 down to 5 of this, which is nothing but again all zeros. Then the immediate field is here, which is 4 down to 1. So 4 down to 1 is 1000. And then you have the 11th bit, which is again 0. So if you now write this up in a proper format, you will see that you will get this particular 32-bit instruction. So that is provided you have written the opcode function rs1 and rs2 also correctly. So then finally you group them into bits, 4 bits each, and then you get the hexadecimal equivalent for the branch instruction. So this is a slightly more complex way in which they have organized the branch instruction. So lastly, you have the J format for the jump. And I think it is obvious why we need a jump in addition to the branch instruction. So the format for jump is in MIPS you had just a J and jump to a certain target. In RISC-V you have JAL, you have an RD destination field, and then you have a 20-bit immediate. Now what does this instruction do? This is going to jump to a certain location specified by the immediate. Again, this is a half word offset. So it is not an absolute target. This is a half word offset, and you're going to add that to the PC as usual. And then you're going to multiply that immediate with 2 because this is a half word offset. And that is the target jump address. And then what is the uh, role of RD? So RD is going to contain the return address. So remember that in a branch, you're going to just branch to the target and not return back typically. Whereas in a jump, you're going to jump to a certain address and then return back because jumps are usually used for procedures or function calls. And so the return address is typically PC plus 4, that is the next instruction following the jump, and that is stored in RD or, for example, in this instruction, it is in X1. So the format for this jump instruction is there is an RD field here, an opcode field, and then the rest of them are immediate fields. Again, the immediate fields are uh, distributed very strangely. The 20th bit, so it's again written as 20 down to 1. The 20th bit is stored here, 19 down to 12, 10 to 1, and 11. So again, this is, I think, in order to be consistent with certain bits in with other instructions. So if you now compare all the instructions that we've discussed so far, I think this will give us a better idea of why they chose to have this kind of instruction formats. So you have the R type, which is the simplest. Then you have the I. The R and I are quite similar up to this particular position. And then you have the immediate field here for the I type. Then the S type, like I mentioned, is also quite similar with respect to the R type. So if you compare RS2, RS1, function 3, and opcode are all in the same positions. Then the B type is a little strange, but then they again have very consistent formats with RS2, RS1, and the opcode. There is also a consistency with respect to the immediate field here. There is a 5-bit immediate here in the B type, and that is similar to the S type. And then you have the U type instruction, again the RD and the opcode are in the same positions, rest of it is immediate. And finally the J type, you have the RD and the opcode, and then the immediates form the rest of the instruction. So they might have probably chosen the 10 down to 5 to be in the same positions in both of these, and that's the reason probably for the particular type of format. So also let us remember that the immediates are always sign extended and the MSB bit is always the sign bit, and they've chosen to have the sign bit in the same positions for all of these instructions. And information about the instructions or RISC-V can be found in the RISC-V specifications or the instruction manual.